Hello friends, welcome to my channel Maths Tutor Lakhyajit. So here this is part 3 of mathematical physics paper solved of BSc first sem and question paper of mathematical physics 2021 set by Dibrugarh University. And in the last part, in the part 2, we have solved up to question number 8a. Now in this video we are going to start from question number 8b. So before we start, please subscribe the channel if you are new to my channel, and share with your friends and hit the thumbs up button. Also hit the bell icon so that you get notified when next part will be uploaded. So now let's start. So here is the question number 8b. So using Stokes theorem, we need to prove that line integral r dot dr is equal to 0. Okay, this r vector is this one, right? So how to prove that? So this is the vector r given in the question. By Stokes theorem, we get that line integral of r vector dot dr vector so is equal to surface integral of curl r vector dot n cap ds, where n cap is the normal unit vector to the surface ds. Okay, so this is suppose question number 1. I have taken this one as question number 1, and here you see curl of vector r. If you evaluate this, then what you gonna have? So if you evaluate the curl, then you can take the determinants, right? So I cap, that's gonna be derivative of z with respect to y, partial derivative, so it's gonna be y 0 again, and derivative of y with respect to that's gonna be also 0. Similarly you can find the others, right? So here you can see here all these terms will be 0. Derivative of z with respect to y, derivative of y with respect to z, as these are partial derivatives, so they are going to be 0. Derivative of z with respect to x, that's going to be also 0. So all the three terms will be 0, right? So as a whole, we will get that curl of vector r is 0. This is equation number 2. From 1 and 2, we can say that line integral of vector r dot dr vector is equal to 0, right? So surface integral of this will be 0 because it is 0 here. So now let's move on to next question. Now starting with the Maxwell equations. This is the Maxwell equation. So apply Gauss theorem. That means here they are talking about Gauss divergence theorem to prove this. Okay, so this is the differential form of Maxwell equation, one of Maxwell equation, and this is the integral form. So we need to prove this one from this equation. So now let me show you. So divergence of E, that is rho by E naught, this is suppose equation number 1. Then by Gauss theorem, Gauss divergence theorem, that gonna be integral surface integral E dot ds will be equal to volume integral del dot E dv, right? So we're gonna get this right using Gauss divergence theorem. So now you see surface integral vector E dot ds vector volume integral rho by E naught. So here you see that here from equation number 1 we have got that divergence of E is equal to rho by E naught. So we have put this value here, right? We have put this value here. So from here from equation number 1 we have got this one. So we can write from equation number 1. So instead of divergence of E, we have put rho by E naught from this equation number 1. So hope you have understood this. So now you see. Now what does rho mean here? This is charge density, right? Volume charge density. And so here rho and E naught will be constant taken outside the integral here, and integration of volume integral of dv will be the complete volume, right? Will be entire volume v. V represents volume here, and we know that volume density rho is equal to q by v. That's why q will be v into rho, right? So rho into v can be replaced by q, right? E naught. So rho into v is equal to q, that is charge, right? So here we have got we have used q is equal to rho into v, right? So this is proved. This is equal to nothing but surface integral E vector dot ds. So this is proved. Now let's move on to next question. Now here is C, question number 8c. Here we need to evaluate this surface integral f dot n cap ds. Here f is given, this one, this is f, right? And s being the surface of the sphere having center 3 comma 1 minus 1 comma 2 and radius 3, right? So here you see this is the given vector f. So let me write that one. Then here s being the surface of the sphere, center 3 comma minus 1 comma 2 and the radius is 3. Okay, so surface integral of this will be given by volume integral divergence of f dv. So it is from Gauss divergence theorem. We have got this from Gauss divergence theorem, right? So now you see divergence of f is given by this. So that's how we can find the divergence of f. So let's find divergence of f. So what are you gonna have? If you differentiate this, if you find a dot product of these two, right, then what you will get? So here you see, if you find a del x of this, then you will get 2 here, and I cap that's gonna be 1. So next, del y of this will be 1 only, 1 into j cap, then j cap again 1, right? Similarly, del z of that one will be only 2. So we have got this. So if you calculate this, it's gonna be 3, right? So we have got divergence f that is equal to 3. Now you see that volume integral, we have got 3 dv. So 3 is taken out of the integral. So dv will be the volume of the this volume integral of dv will be the volume of the sphere. So we know volume of a sphere is given by pi 4 by 3 pi r cube, right? 4 by 3 pi r cube. Volume of a sphere of radius 3. So volume of a sphere is 4 by 3 pi r cube. So here the radius is 3, that's why it will be 4 by 3 pi r. Instead of r, we're gonna put 3 cube, right? So if you do so, then what you will get, 3 into 4 by 3 pi into 3 cube. So here this 3 cancels each other, then 3 cube, that's 27, and 4 is 108, I think, right? 108 pi you're gonna have this. So this is the this is how we can evaluate this, right? So hope you have understood this. Now let's move on to next question. Now you see, define orthogonal curvilinear coordinates. So how to define it? Suppose here, let us suppose that the rectangular coordinates of a point xyz, suppose, of any point in space are expressed as function of u1, u2, u3. Say small x is equal to capital X of u1, u2, u3. Similarly, small y, capital Y of this one, and small z, capital Z of this 3 again. So this is suppose equation number 1. If you solving one, we can get the values of u, v, w in terms of x, y and z, such that small u is equal to capital U of x, y, z. Similarly, small v is equal to capital V of x, y, z, and w, small w, capital W of x, y, z. Then this small u, v and w, these are called curvilinear coordinates. Now here you see the point xyz, the surface, the curvilinear, here you see this is called these are called curvilinear coordinates of this Cartesian coordinate xyz, right? So these are u, v, w, these three are curvilinear coordinates. Now the definition is not completed here. Now if you take the surfaces u, c1, v, c2, c3, so here c1, c2 are constants, right? These are constants, and u is equal to c1, v is equal to c2, and w is equal to c3 represents surfaces, right? So here you see each pair of these surfaces intersect in curves, and those curves are called coordinate curves. And if these coordinate curves surfaces intersect at right angle, then u, v, and w are called orthogonal curvilinear coordinates, okay, of the point x, y, z. That means here you see the surfaces represented by u, c1, and v, c2, and w, c3, they must be mutually perpendicular, right? Then these three coordinates, curvilinear coordinates, will be called orthogonal curvilinear coordinates. So this is the definition. So hope you have understood this. And if you have understood, please share with your friends and hit the thumbs up button, and press the bell icon if you are new, and stay connected. Next part will be coming soon, okay, where the paper will be completed, okay. So I have not completed yet, so paper will be completed in the next video.